Go.
Hello, my dear students, and welcome to the last video help session for Chapter 3. We're continuing to talk about mole ratios. We've talked about limiting reagents or reagents present in excess. Same concept. But now we're going to talk a little bit about using mole ratios, not necessarily to calculate percent yield, but to see how they're used maybe in a little more practical way. This exercise starts out with building on what we've already done. Specifically, my periodic table fell down. I thought that was enough tape for it. And I will get some more magnets holding it up now. There we go, that's the strong one. And we'll look at how much product is made when we underdo a combustion analysis, burning in oxygen, of 4 quick compounds. Only because this has historical significance for how we determine the composition of complex molecules. And some of the complex molecules we'll look at are styrene, the component of polystyrene, the plastic, the hard plastic, used in toys and all kinds of things, automobiles. What else? Aniline, used in aniline dyes. Aspartame, the sugar substitute, and what else was there? Penicillin G. So let's go straight to those and look at them. And then I want to quickly show you some sample problems I put in there that were taken actually from last year's test. So you can expect to see them again. So it says, how many moles of carbon dioxide and water will be produced by combustion analysis of 0.01 moles of styrene? So let me take off this old problem. That was one we did where we were looking at empirical formulas a long time ago. So if you look at this structure of styrene, you'll see it's a ring structure. You'll see it's a ring structure of carbon. And I'm not going to draw them all out because you have them all there with you. This particular one has a ethylene chain attached to it with hydrogens completing all the last bonding valence of the carbons. And you have a variety of ways you have a variety of ways you can calculate the molar mass and, in this case, the molar composition of styrene. Okay? So this is styrene. That's a bit of a trivial name, but it's in common use for this compound. Very common feedstock chemical. But if you look, it has 1, 2, 3, 4, 5, 6, 7, 8 carbons, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And in fact, it has the empirical formula CH. But what this means is, for every mole of styrene, when I combust this with excess oxygen, I'm going to burn this and make CO2 and water. And for every one of these, I'm going to make 8 of these. And for every 2 hydrogens, I'm going to make a water. So I'm going to make 4 water. Okay? So my balanced equation would be one of these plus, what's this? 8 9, 10, plus 10 oxygens will give me 8 carbon dioxide and 4 waters. But here's what those are. Those are molar ratios, okay? These are my coefficients in my balanced chemical equation. Just like an algebraic equation where if you have 3x plus 2y equals 14. That 3 in front of the 3x and that 2 in front of the 2y are your coefficients. And it's the same thing here. We use those to calculate our mole ratios. So this problem said I had 0.010 mole of styrene. And I'm doing a combustion analysis. That means this is in excess oxygen. 0.010 moles of styrene. So I didn't have 1 mole. I had 0.010 mole. And we know that here the ratio for making CO2, it says how many moles of CO2 we produce. For every 1 mole of this, we make 8 of those. So all I need to do is multiply this times 8, and I'm going to make 0.080 mole of carbon dioxide. That's your answer. And for every 1 mole of this, I'm going to make 4 moles of water. So how much water am I going to make? 0.010 mole times 4, using my mole ratio. That's equal to 0.040 mole H2O of water. That's your other answer. Those are your 2 answers. This is your calculations. Now, if it weren't this easy or straightforward, you would still want to do mole ratios. How do you do that? Let's do it for the water. The one we just did. This says 1 mole of styrene. I was going to write C8H8 because it's quicker than writing styrene. Gives me 4 moles of water in my equation. So the way we do this is we set up our molar ratios. This is true all the time. It always has to be in this ratio because these were the coefficients from our balanced equation. So if I have 0.010 mole of polystyrene, the question is, how many X mole of water will I get? So we cross multiply. 1 times X equals 1X. And here's our cross multiply this way. That has to equal to 4. That's a 4. Sorry, I'm at the bottom here. Times 0.010. So that means X equals 0.040. So to do it strictly and mathematically, the X for the X number of moles of water is equal to 0.040. We're just going to talk it through from now on. But if you want to, you can set up those mole ratios. The next one asks, if I do a combustion analysis for aniline. Now this is a ring structure compound, and it's not giving you the formula, it's giving you the structure. So you have 2 choices. You can count 1, 2, 3, 4, 5, 6 carbons, 1 nitrogen, the blue one, and 1, 2, 3, 4, 5, 6, 7 hydrogen. So in this case, my aniline dye, not aniline dye, but just my aniline, the starter compound for many dyes and other compounds, is C6H7N. If you don't want to look it up or you can't interpret that structure, Google it. Google aniline, molecular formula or chemical formula. This is its chemical formula. And it says I started with 0.0080 mole. So now, it said how much carbon dioxide, water, and nitrogen will be made. So for every mole of this, there's 6 moles of carbon in every mole of aniline. This was that aniline, is its trivial name. This aniline, 1 mole of this will give me 6 carbon dioxide. And 1 mole of aniline will give me 7 moles of hydrogen, but that can go on to make 3.5 moles of water. And this can go on to give me 1 mole of nitrogen for every mole of aniline, because there's 1 in this compound, but it asks how much nitrogen gas will be produced in this combustion analysis. So nitrogen gas is diatomic. It even says N2 here. So I only have 1 N, so it's going to make 1/2 a mole of N2. Okay? If you have any problem with that, call me, not call me, but text me or email me, and I can go into more detail or do supplemental video help sessions. But we were reacting this, and for every mole, we can go to molecules. Every molecule of aniline gives me 6 atoms of carbon. Those can go on to make 6 moles of carbon dioxide. Every mole of aniline will give me 7 moles of hydrogen, or 3.5 moles of water, because I need 2 hydrogens for every water. And every mole of aniline will give me 1 mole of nitrogen, but I need 2 of those to form a mole of nitrogen gas, so I'll really only get 1/2 a mole of nitrogen gas for every mole of aniline. And the question is, if I start with this much, how much will I produce? This is just, can you do it? Can you make those decisions and calculations fairly quickly, and hopefully in a straightforward manner? But in combustion analysis, this is what we do. We count how many moles are made, and we work backwards to deduce the formula. We don't do it much anymore because now we use more sophisticated techniques like mass spectroscopy, but a mass spectrometer to determine composition. But historically, this is how all these structures, complex structures, look at them, were determined. So, how much nitrogen will I produce? Half as much, or 0.0040 mole of N2 gas. How much water will I produce? 3.5 times as much. I did the calculation right here. I'm not going to multiply 8 times 3.5 in my head. What would that be? 3 times 8 is 24, and another half of 8 is 28. So that's 0.028 mole of water. And then for the carbon dioxide, I just multiply 0.008 times 6, so that's 0.048 mole of carbon dioxide. Page 1. This is a longer one. It's 4 pages long, but I'm going to go quickly from now on. So, the next 2 ask first for aspartame and then for CO2. Now, I did not know the structure of aspartame. It's right there, and I said, there's got to be an easier way. There is. I just Googled it. But then I thought, you know what? That's cheating, so I went ahead and counted them up. And if you count up my aspartame, I'm going to change colors now. Should do a blue one, because aspartame's always blue, right? In the little blue packets. Aspartame stands for asp-methyl ester, which is the amino acid aspartic acid plus the amino acid phenylalanine plus its methyl esterified. So aspartame, asp-methyl ester is its formal name. Anyway, it's got if you count them, and I did, 1, 2, 3, 4, I had to count it 3 times, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. This is number 3. It's got 18 hydrogens. If you look closely, you'll see 2 nitrogens and 5 oxygens. And it asks, if we start with 0.0074 moles of equal, the sweetener equal, that equals the sweetness of sugar, aspartame, like I said, the stuff in the blue packets. If we start with this many moles, how much will we make? Well, for carbon, we'll make 14. So for CO2, it's equal to 14 times 0.0074, and that's equal to 0. I can't read my own writing here. Not sure what I've done here. It looks like 0.36 mole of CO2. Somebody check my math on that. For the H2O, 18 atoms of hydrogen will be produced, but that will only produce 9 moles of water. So 9 times 0.0074 moles of aspartame is going to produce 9 moles of water, and I got 0.066. I need my calculator. Excuse me. Just keep focused on that, and I'll be right back.
Okay.
I'm sorry, I should have had my calculator handy, or I should have printed more neatly. TI-84, 14 times 0.0074, fat fingers, 14 times 0.0074 is equal to 0.1036. I knew that value had to be higher than the previous one. That's why I was mistaken. Okay, and this is 0.00666 mole of H2O, and it asks for nitrogen, so N2. So for every mole of aspartame, I make 1 mole of N2, because there's 2 nitrogen atoms in that structure. They're the blue ones if you print your problem out or look on the screen in color. And so that's 1 times 0.0074, which is equal to 0.0074 mole of nitrogen gas will be produced in your combustion analysis of this compound. And 1 mole will be produced for every mole. And if you start with 0.0074 moles, you'll make that much. So now this second part to this question takes us back to the assignment that you had at the beginning of this chapter. And that was our assignment, or exercise 3.1. We had a series of equations, and I asked you to balance them. And so, if you look at this, this is a question from a test from last year. I just copied and pasted it. Series of questions, renumbered them to fit the pattern. But even back then, when I was putting equations on the test, I was taking equations right off the homework, because they got that same homework. This is a homework by NIMSI, National Math and Science Initiative. funded by the Walton Foundation, since we're in Arkansas, as well as the Bill and Melinda Gates Foundation. I guess it's Bill Gates and the former Melinda Gates. I don't know what her name is now. But they are both, despite their difficulties, wonderful philanthropists. And I asked you to balance this, and you saw that when we balanced this, I had 2 irons combining with 3 sulfuric acids to give 1 iron sulfate, common ingredient in iron pills and iron-enriched vitamins, and 3 hydrogen gases. And I took this, and what did I do? For testing purposes, and for this, I labeled this one A, this one B, this one C, and this one D. And the first 4 questions are the way I ask this on a test in an objective multiple choice way. And that is A, B, C, and D. And I ask, what is the value of A? You know, and your choices would be like A1, B2, ding, 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 C3, D4. But the first one says, what's the value of A? It's a 2. Because this is an assignment, not a test, so I didn't give you multiple choices. What's the value of B? It's 3. What's the value of C? It's 1. And what's the value of D? It is 3. Now, if I may, is there anything underneath this? What I really need is a piece of paper to put under this. Let's see if I can sneak one out. I can't. Oh, you know what? This one's already hot the way I need it. So, we'll just hang it right here and remember that, okay? So it says, how many moles of hydrogen gas would be produced if 1 mole of iron was reacted in excess sulfuric acid? So forget limiting reagents and excess reagents. It says I have plenty of this. And now, this is my balanced equation. Now, instead of 2 moles of iron, okay, this asks what would happen if I had 1 mole of iron. Well, that's half as much, so I'd produce half as much hydrogen gas, or 1.5 moles. That's great if you can think like that and think that fast. Let's do it the right way. In this equation, 1 mole of iron reacts to form 3 moles of hydrogen gas. 1 mole of iron, solid iron, when dissolved in acid, produces 3 moles of hydrogen gas. That's from the balanced equation. That is my mole ratio. But, as often happens in life, you don't have perfect balance. And we're not going to start with 2 moles of iron. Oops, I'm sorry. Oh! This is too important to not stop and back up. In my balanced equation, every 2 moles of iron give me 3 moles of hydrogen. The question asks, what would happen if I only started with 1? Well, I set up a mole ratio. I don't have 2 moles, I have 1 mole of iron. And the question asks, how much X moles of hydrogen is going to be produced? Okay? So, the formal way to do this is to set up your mole ratios and cross multiply. So 2x is equal to 1 times 3. So 2x equals 3, so x equals 1.5 mole H2. So this x is equal to 1.5. That's your answer. That's for number 5. For number 6, let me keep setting these ratios up. This is going to be a constant. 2 mole of Fe reacts to give 3 mole of H2. That is my mole ratio for this balanced equation. It's the value I'm going to use every time. And it doesn't matter which one's on top, because when I cross multiply, it's all going to work out, as long as I keep my next one the same. And now it says, what would happen if I use 3 moles of iron? Then how many moles of H2 would I get? Well, I cross multiply. 2x equals 3 times 3. So 2x equals 9. So x equals 4.5 mole of hydrogen gas. Ta-da! This x equals 4.5. So if I start with 3 moles instead of 2 moles, I'll end up with 4.5 moles of hydrogen. That's all it says. I worked for Celanese Chemical Corporation, which transmogrified at least my group into Celgene, the biotech company, but was bought by the giant German chemical company AG Herbst. They're famous for Celanese 4-triol polyester, but they were one of the world's leading chemical companies behind only DuPont. Okay? And this is what they did. If I start with this much, now I might, they didn't start with moles, they started with train cars, but they want to know how much of something they made, because that's how they made their money. Because when they make chemicals and then sell them, they're making money. So, this is what chemists do. They want to know how much they're going to get. And the other thing they want to know is, how much do they need? If I want to make this much, how much of this do I need? So, number 7. Let me change colors so that I keep everything separate and a little more organized. This says, how many moles of hydrogen gas we produce if 4 moles of iron was reacted? Can you tell that's twice as much? So instead of starting with 2, I'm starting with 4. But let's do it the formal way. Set up my mole ratio. 2 moles of iron always gives me 3 moles of hydrogen in a balanced reaction. And if I start with 4 mole, how many would that give me? And I'll show you in a minute why setting up your mole ratios is important until you've done this a lot of times, so you don't do it in your head. Because if you're like me and you're doing it in your head, you'll make mistakes. You see me trying to talk, trying to explain it, writing it up here, trying to keep it straight, making mistakes. So easy to make a simple mistake that up here ends up ruining everything down here. So all I can say is, yes, these are straightforward, but they're not easy, because you have to do every step perfectly. So here I have 2x equals 3 times 4, so 2x equals 12, so x equals 6 mole of hydrogen gas. And you're say, well, that's of course, because that's 2 times 3, and you started with twice as much iron, so you should end up with twice as much hydrogen. True. But what if we, I don't know, do something that we can't do in our head? I'll show you that next. Just going to move this down so I can do one more, and then we'll move over to the board and do a longer problem. So number 8 asks, ooh, green and red, got some Christmas colors here. If I start with 5, so my mole ratio is 2 moles of iron to 3 mole of hydrogen gas. Every time I do this reaction, 2 moles of iron produce 3 moles of hydrogen in our balanced chemical reaction. But now it asks, you're starting with 5 mole. Okay? So, and now I want to know how many moles, x mole of hydrogen will I produce from that 5 moles of iron? Well, just look at this. 2x equals 3 times 5. Cross multiply. I'm cross multiplying here. Okay? So, 3 times 5 times 5. And that means 2x equals 15. So in this case, x equals 7.5 mole of hydrogen. That's your answer. Not H2O, just hydrogen gas. There's the answer. Okay. I get to see on a test. Can you do that? That's question number 1. Question number 2 is, can you do it if instead of saying 5, I say 6 or 7? And the next one is a lot like number 5, except it says how many moles of hydrogen gas would be produced if instead of starting with 1 mole, if I may, so this is also number 9, I started with 10 moles. I'm going to jump ahead and take the shortcut. If 1 mole gave me 1.5 moles of hydrogen, then 10 moles would give me 15 mole of H2. If 10 mole of iron. Okay? If I start with 10 times as much, I end up with 10 times as much. So I will take the shortcut. If I want to make sure I get it right, like in a testing situation, that's okay for homework. But when we were calculating quantities at Celanese, I visited a Celanese plant in Texas, I want to say down around Victoria, that produced 1 million gallons of acetic acid, not vinegar, that's like a few percent, concentrated acetic acid a day, 1 million liters a day. I'm sorry, 1 million liters a day. Think metric. I don't even know where you would put 1 million liters. They put it into tank cars. But here's the deal. After you put that 1 million liters in the tank cars, the next day you produce another 1 million liters, and you need a lot more tank cars. It's incredible. So, you know, the quantities and the amount of money involved is almost unimaginable to us. So, let's talk about what would happen if I wanted some hydrogen gas. It's a great syngas and it's a great fuel. Let's say I wanted to use this to fuel a hydrogen fuel cell, which are, according to many people, the future of alternative energy, because you can use solar energy to produce hydrogen. You don't need to worry about the lithium in the world running out. And all you do is split water to get hydrogen and oxygen gas, and then you react that hydrogen gas, either burn it, which requires pressure and combustion engines, or you use a fuel cell and react it and extract energy from it that way. Either way. But now, let's just say for number 10, this is the difficult one. I'm not going to tell you how many moles I'm starting with, because you know what? When I go out and dig up some iron or recycle some iron or buy some iron, I don't buy moles. I buy a certain mass of it. And let's say I have 100 grams of iron. Okay? This would not be the way to produce hydrogen gas, but if this were. And the question is, how much hydrogen gas will I make? So, according to this equation, according to our balanced equation here, where I react elemental iron with sulfuric acid to produce hydrogen gas, and always go through the mole. That's why I spend so much time on the mole concept, because it's central. Being able to work with moles and do mole conversions is central to being a good chemist, because it's something you have to do for just about every problem from now on. So 100 grams of iron, if you look, I need to convert that to moles. And I'm looking over here, can you zoom around here at my periodic table? Iron is right here, but they also chose iron for the example for the key. It has a atomic mass, molecular mass, it's not a molecule, of 55.845. So 1 mole of iron weighs or is equivalent to 55.845, because I want to substitute moles for grams to answer my question. And this is multiplying this value by 1, because 1 mole of iron is the same as 55.845 grams of iron. And if I do the math, and I've already done it, so I'm not going to take time, that turns out to be 1.791 mole of iron. You really don't need to go to that level of precision, but since I used a periodic table and got a very accurate value for this, and since my question says it's 100.0 grams of iron, so I have 4 significant figures, I can have 4 sig figs. Now, notice what I'm talking about. I'm going back and talking about concepts we learned earlier, because this course builds. You know, I didn't hit you over the head with significant figures, and yet, you know, I warned you, we're going to be using them and considering them all along. So I have 4 sig figs here, and 1.791 moles. It's the same as these. Uh-oh, not even numbers. Who cares? For every 2 iron, I produce, that's an E, sorry, 3 hydrogen. So what happens if I start with 1.791 irons? How much hydrogen will I produce? The same thing. 2x, cross multiply, 2x equals 3 times 1.791. And solve for x. 2x equals 5.372. So x is equal to 2.686 mole of hydrogen gas, which is a fun gas to have and play with, as long as you don't have too much of it or you're not riding in a Zeppelin or blimp filled with hydrogen gas, explosive hydrogen gas. So, if I might, for those of you coming up at midterm and saying, this is really hard, this is as hard as it gets, okay? This is the hardest, most sophisticated work we're going to be doing. We are going to be saying, okay, I have 2.86 moles of hydrogen. What would be its volume at standard temperature and pressure? Because I haven't worked problems or dealt with this very much, only mentioned it once, but in our mole conversions where we convert mass to moles or number of particles to moles and back and forth, for every gas at standard temperature and pressure, as I alluded to when I first described the mole in Avogadro's work, every gas at standard temperature and pressure, 0 degrees, I guess it was cold back then when they set this up, and sea level, every gas has a volume of 22.4 liters, 1 mole. 1 mole of any gas at what we call STP, standard temperature, is 22.4 liters. So we can do those kind of conversions. And if we make it all the way through the gas laws, you'll also see, but what happens if it's not at 0 degrees? Or what happens if I'm in Arkansas, 50 feet or 150 feet above sea level? Then we can make those conversions too. But determining how much I need, or given this much, much can I make? Or given this much, but I only have so much of this limiting reagent, how much can I make? And the mole ratio concept will get you through an awful lot in chemistry. And As far as I'm concerned, it's one of the most difficult, most sophisticated things, and yet just lay it out. Make sure you start with a balanced equation, but once you have that balanced equation, you can set up your mole ratios, and knowing that you can convert back and forth between molar mass and moles and number of moles and number of particles, you can calculate anything we need to calculate at this point in the course. And it's about as difficult as it can get. So don't drop. And we'll move on to chapter 4. If you haven't already, I don't know what's posted yet or what I've gotten posted, but until chapter 4 and the exercise associated with chapter 4, stay safe. Goodbye now.